In the recent years, the growing interdependence between electricity and gas networks has led to a greater focus on the research and development of the integrated operation of gas and electricity networks. At the same time, the network operation is complicated by the rising number of uncertainties introduced by the intermittent renewable generation, such as more accurate and efficient methods for assessing the system adequacy. Probabilistic methods, which are generally employed to deal with uncertainty, can be computationally inefficient because of the consideration of a large number of uncertain parameters, especially in larger networks. Therefore, the objective of this work is the efficient identification of the most critical uncertain parameters that impact the system adequacy. In this work, system adequacy, abbreviated by Z, is defined as the sum of conventional generation and renewable generation subtracted by the total electricity demand. The identification of critical uncertain parameters is performed using three sensitivity analysis techniques. The first is the one-at-a-time method, the second is the correlation-constrained Morris method, and the third is the Spearman correlation method. The Spearman correlation method is considered as the benchmark method because it employs the largest search space among these methods. It more accurately determines the impact of a given input on the system output. However, it also requires a very large number of simulations, which makes it computationally inefficient in larger electric energy networks. Therefore, it would be valuable to examine the relative accuracy of the one-at-a-time and Morris methods, both of which require significantly reduced number of simulations and computation time. The OAT method determines the sensitivity of the system output to input parameters using a local search. This method studies the impact of a small variation in one input at a time on the system output and determines a normalized linear relationship between the parameters in the local region around the nominal operating point. The results are thus strongly reliant on the selected search space. A larger value of the sensitivity index means a high impact of the input on the output. This method requires low computational time and simulations. For example, it only requires p plus 1 simulations for p uncertain input parameters. However, its application is unsuitable when the system is nonlinear or when the system output is impacted by a combination of input parameters. The Morris method determines the sensitivity of system output to input parameters using a screening process. The traditional Morris method neglects the correlations between input parameters, so the regions of the search space with low joint probability density could be used in determining the sensitivity. This can produce inaccurate results. To modify the Morris method and consider the correlations, a boundary constraint is introduced within the trajectory generation process using the Mahalanobis distance. First, the search space is divided into discrete steps and an initial value is randomly selected for each input parameter, resulting in the base point of the trajectory generation. Subsequently, a random walk is performed along a trajectory through the search space. Each step of delta is randomly taken given that the boundary constraint is not violated. The Morris method requires p into r plus 1 simulations for p input parameters where R is the number of levels per dimension, which normally ranges from 4 to 10. The Spearman correlation method determines the sensitivity of system output to input parameters using a global search. Since the Spearman method may require a large number of simulations, a stopping rule is used to limit the number of simulations. In this method, the input uncertainties are modeled using suitable probability distributions. Beta distribution for photovoltaic power, Weibull distribution for wind speed, which is then converted into wind power using the speed to power function, and Gaussian distributions for electricity and gas loads. The test network is an integrated 9-bus electricity and 8-node gas network, coupled through a gas-fired power plant and an electricity-driven compressor. The sensitivity of electricity system adequacy is investigated considering 11 uncertain input parameters, which include 3 photovoltaic farms, 3 wind farms, 3 electricity loads, and 2 gas loads. 3 test cases are considered with 30%, 40%, and 50% renewable energy penetration, respectively. The renewable energy penetration is calculated as the percentage of peak electricity demand. The probabilistic modeling of uncertain input parameters and the sensitivity analysis are performed in MATLAB, while the integrated gas and power flow simulation is carried out using MATPower natural gas platform. The figure on the right-hand side shows that the correlation coefficients between the input uncertainties in Morris method and the Spearman method. The scatter plots demonstrate that this Morris method captures the input correlations as effectively as the Spearman method. To implement the one-at-a-time method, a 10% variation in each input parameter is considered. In all the test cases, the top 3 critical parameters are the electric loads, mainly due to their relatively large magnitudes. On the other hand, the sensitivity indices for the wind and photovoltaic farms remain considerably low and unaffected, showing that this method is unable to address the uncertainty associated with the increasing renewable penetration in case 2 and 3. Please note that the absolute values are considered for the sensitivity indices of electricity and gas loads. In the correlation constrained Morris method, the electric loads are highly ranked in all the test cases, mainly due to their comparatively large magnitudes. However, the wind farms are ranked significantly higher in case 2 and case 3, showing that the Morris method effectively captures the uncertainty associated with the increasing renewable penetration. In the Spearman method, first, the number of simulations required to ensure that system uncertainty is suitably captured is selected using the stopping rule. The simulations are stopped when there is 99% confidence that the error in sample system adequacy mean is below 1%. This occurs when the number of simulation is 1244, 1483, and 1849 in case 1, 2, and 3 respectively. The results for the ranking of input parameters based on the Spearman method show that the critical parameters identified are identical to the Morris method in all the test cases. The comparative evaluation of the results show that the Spearman method provides the most accurate results as it employs the largest search space and analyzes multiple input parameters at a time. In comparison, the one-at-a-time method is much quicker but produces inaccurate results. The parameter ranking based on the Morris method is identical to the Spearman method, but with a significantly reduced computational time because it shrinks the search space through its screening process. This is a valuable result since the Morris method provides a more efficient alternative to the Spearman method. Based on the obtained results, the most critical uncertain input parameters were the electricity loads and the wind farms, whereas the gas loads and the photovoltaic farms were comparatively non-critical. The uncertainty associated with non-critical parameters might be ignored during further network analysis to gain significant improvement in computational efficiency. It was also demonstrated that the correlation constraint Morris method provides identical parameter ranking compared to the Spearman method, but with a significantly reduced computational time, making it more suitable for application in larger energy networks with large sets of uncertain input parameters.